Well, thank you everyone for coming again to Friday seminar. Hope everybody's week has ended well. Today we have the pleasure of having Dr. Larry Swanson from the School of Marine and Atmospheric Sciences at Stony Brook University, where he is the Associate Dean of the School of Marine and Atmospheric Sciences and the Director of the Waste Reduction and Management Institute. Larry's experience and research interests are definitely varied. He actually started his career in the Coast and Geodetic Survey and retired after 27 years as a captain in the NOAA Corps. He received his master's and PhD from Oregon State University, and today we'll be hearing about his research from the Long Island Sound study with a talk titled Understanding Hypoxia and the Need to Improve Monitoring in Long Island Sound. So thank you very much for coming up today.
Thank you. Thank you very much. It's a pleasure to be here, and I must say I've been impressed by wandering around here just for an hour or two and just seeing what is going on in charting, because I haven't kept up with it very much, as you can tell, because I'm starting with an old map. This is a map that goes back to 1670, and it's at the New York Historical Society and very close to the Natural History Museum. And the reason I wanted to put it up was that we think this is the first time that the term Long Island Sound was ever depicted on a map. And for those of you that are familiar at all with the coastline of Long Island, you can see that they have really very nicely depicted most of the headlands in the Sound and most of the features along the Connecticut coast. So it's indeed impressive. And here's the scale. This is in English miles, which is essentially our statute mile. But I want to talk about hypoxia and the need to improve monitoring. So for those of you that don't deal with hypoxia every day, let me just say that we define it in very different ways, depends on where you are and who you talk to. New York State, we talk about it as being dissolved oxygen concentrations less than 3 milligrams per liter. And in Connecticut, it's less than 3.5 milligrams per liter. US EPA now uses an integration of concentration and time. So it's quite variable. Anoxia, on the other hand, is no dissolved oxygen. So what I wanted to do today was just point out to you that Long Island Sound is an unusual estuary, define hypoxia a little bit, show you some of the monitoring that is going on in Long Island Sound, specifically dealing with hypoxia, talk about climate and how it's affecting hypoxia, and I'll give you two examples of sort of the complexity of the physics of hypoxia, and then hopefully we'll be able to talk a little bit about the need for improving monitoring. Just like before I go on too much, the United States has spent a lot of money upgrading sewage treatment plants. That's where I get into the waste business. And what they do is they define something called a total maximum daily load, TMDL. And in the case of Long Island Sound, hypoxia was identified as the most severe problem that they were confronting as compared to, say, with chemical issues and what have you. And the solution to the hypoxic problem in Long Island Sound has been to impose TMDLs on point sources and non-point sources. And it's costing billions of dollars. So one of the things that I think we need to do is understand the complexities of the physics of these water bodies as it relates to issues like TMDLs determinations, so that we don't throw money down the rat hole, so to speak. So Long Island Sound is unusual in that it has an entrance to both at its mouth out at the race in eastern Long Island Sound, but it's also connected to the Atlantic Ocean through the East River very unusual for an estuary. The major source of fresh water, unlike what we mostly think about with estuaries, happens to be close to its mouth, and it's the Connecticut River. The East River is a tidal strait, and the long-term flux of salt is upstream or through the East River out into the Atlantic Ocean. The long-term net flux of water is also toward the harbor. The net flux of fresh water, however, is from New York Harbor into Long Island Sound. So this is very unusual because you ordinarily don't think that there is a net flux of salt or water upstream in an estuary. Otherwise, we get constantly be faced with getting saltier and saltier all the time. It's also unusual in its geomorphology. It's the deepest east coast estuary. It's never been dredged in its main channel for the purposes of navigation. It's typically on the order of 30 to 35 meters deep. It's not a coastal plain estuary, like it's not a drowned river valley like like the Chesapeake Bay or the Hudson River. It was shaped by glaciers. It has a sill near its mouth, but it's not like the typical sill that you think of if you're talking about a basin such as Puget Sound. It's not crystalline, it's a sediment deposit. Its flanks are dissimilar. The Long Island side is basically rubble from glaciation, and the Connecticut side is crystalline rock. And it's also unusual in that the thalweg, or the deepest part of the estuary, is essentially parallel to the coast instead of incising the coast. So for those of you that don't deal with eutrophication and hypoxia every day, I just thought I would put this up. A set of physical and chemical and biological changes brought about when excessive nutrients are released into the water. In our neck of the woods, our part of the world, nitrogen is considered to be the limiting nutrient, and as a consequence, that's what we're faced with trying to manage, as opposed to, say, phosphorus. The oxygen demands in the water column are both living and non-living. The sediments have oxygen demands. Of course, the benthic organisms have oxygen demands as well. And we only have 3 ways of getting oxygen into the water column. It's mixed at the sea surface, or it can be created by photosynthesis, or it can be advected. The first 2 only take place in the surface of the ocean. The last can take place at depth. So, for example, if we had oxygen-rich water in Block Island Sound that is just to the east of Long Island Sound and it's in the bottom waters, estuary transport or gravitational flow could transport that oxygen-rich water into Long Island Sound. This is just a diagram of the general process of what we're dealing with. Here we've got the stratified water column, the warmer, fresher water at the surface, the colder, deeper water at the bottom. We got the little critters doing their thing, creating fecal pellets and so forth. We got organisms living down here and dying down here, consuming oxygen. And then we put nitrogen into the water column through sewage treatment plants and through runoff. And in our area, we've done a lot of fertilization for farming and what have you that gets into Long Island Sound and has created some problems. So this is what we're trying to manage, but there's a lot more going on in this area that has to do with the physics, and that's what I really want to focus on. So this represents a typical summer bottom dissolved oxygen concentration map. And all these little numbers, the state of Connecticut goes out about every 2 weeks and lowers a CTD with bottles and so forth to monitor what's going on. The black represents basically anoxic conditions, concentrations of dissolved oxygen of 0 to 1 milligram per liter. The red is 1 to 2 milligrams per liter, and the gold is 2 to 3 milligrams per liter. The green is pretty healthy waters. So you can see that a fair portion of Long Island Sound is potentially hypoxic, and this occurs regularly during the summer months. So I'm going to talk about this area down here, but I'm also going to talk about this area. This area is of particular interest because there really are no major sources of contamination or pollution going into it. There's not a major sewage treatment plant. This is all low density development around here, but yet this sticks out like a sore thumb every summer. So the question is, what's going on there? This area down here, closer to the city, has 4 major sewage treatment plants from the city discharging it just to the west of it, and they contribute about 1 billion gallons of secondarily treated sewage every day. And at times, if in a very dry year, some 25% of all the flow in the East River could have flowed through a sewage treatment plant. So there's a lot of sewage. New York City generates about 1.5 billion gallons of sewage every day, and it all goes out into either New York Harbor or the East River. This is another monitoring program. This is run by a colleague of mine at the University of Connecticut, Jim O'Donnell. He has a series of continuously operating buoys here in the western Long Island Sound, more towards the east, and then some of the tributaries. So one of the things to think about as I go through this is that we're constantly faced with budget issues, just like everybody else is. We have a monitoring program in place that is fairly well funded. The state of Connecticut runs it, but they don't want to change it. They're, happy with it. It's providing jobs and so forth. But one of the questions I think we have to ask, based on what we now know about hypoxia, is there a better way? Can we make more efficient use of the resources that we have in order to better understand the consequences of hypoxia and how to improve it? Jim's buoys are nice in that they provide continuously recording data if they're working. And that's always a question. Remember, the Connecticut's data is collected at the best every 2 weeks, usually during working hours, so it's in daylight hours, and so you're not really representing the cycle of dissolved oxygen and its use very well. So now I want to talk about some of the changes that we're seeing with climate and the potential impact that it will have on hypoxia. It's hard to believe, but in the early 1800s, when steamboats were first introduced to the area, the East River was closed virtually every winter over the period of November to March by ice. In fact, they recommended boats not go through it. And the local residents actually were very happy with that because Brooklyn Bridge didn't exist. They could only go to Manhattan via ferry from Brooklyn. And so when it froze over, they could walk. They didn't have to pay a fee to get on the ferry. So they were very happy with that. I'm not sure we'd be happy with that today. Closer to now, though, there's something to start being concerned about, and that is, if you look at New England rivers, the center of flow, or essentially the peak discharge, has backed up in time about 2 weeks. And when I mean back it up in time, let's say that on the average 50 years ago, The peak discharge of these New England rivers was in March, around the 1st of March. Now it might be mid-February. So that's what I mean when it's backed up. And this presents a very serious issue with regard to the development of hypoxia in Long Island Sound. And here is illustrated with a diagram of peak discharge from the Hudson River. This is 1950 to 2010. On the bottom, the vertical axis is the peak discharge, the month of the peak discharge, and this is in water years. So U.S. Geological Survey calls a water year, beginning of the year is in October. So this is October, month 6 is March, and month 7 is April. And you can see going back the 50s through much of the 80s that oscillated between April and March. Beginning mid-1980s began to vacillate quite a bit, and actually it's occurring much earlier now than it has historically. And this is clearly an effect of climate. Whether you want to call it climate because of people or not doesn't matter. The simple fact is that the amount of snow that we have in upstate New York and in New England has declined over the last 15 or 20 years or so. So this is backing up in the Hudson River when the peak discharge actually is occurring. And the Union of Concerned Scientists say that in this century, the amount of the snow season could be cut in half. So we can anticipate, just thinking about only hypoxia, that there could be some very interesting consequences from this. And here are some of them. We're going to get earlier stratification of the water column. Long Island Sound, we begin to get stratified waters because early in the year, in March, April, Connecticut River peak discharges typically occurred. The Hudson River discharges started to occur, and so we get a lens of fresh water forming on the surface of the sound. Gradually, that dissipates and temperature becomes a controlling factor. So by July, the sound is well stratified, inhibiting the mixture of dissolved oxygen from photosynthesis and from the atmosphere from getting to the bottom. And if we're going to start stratification earlier in the year, then we will have a much longer stratification season. We'll get reduced water column mixing, because essentially the only mixing that takes place is due to wind mixing, and that is between the surface and the picnic line, or the area where the density of the water column changes rapidly. It'll shift the timing of the input of carbon and sediment to Long Island Sound, and as a consequence of that, it will change water column transparency. This will have a potentially interesting impact on photosynthesis. If we are not getting the large suspended sediment load that we get from the peak discharge in April and March every year, and it backs up in time, it means that the water column is going to be clearer earlier in the year, and as the days begin to get longer, we're going to have photosynthesis taking place more effectively than it currently is. And then it clearly will have a change on the gravitational flow or the estuarine flow of Long Island Sound as well. Another thing that we're observing is that the winds are significantly changing. And pay attention just to the bottom here, because I think it's a little clearer, and it's actually more important with regard to circulation in the sound. The blue line represents the wind in knots as measured at LaGuardia Airport in western Long Island Sound from the period 1947 to 1977. The green is 1977 to 2007. Well, you notice in the blue that the minimum value occurs about day 130, 135, something like that, in the early part of the record. We now reach that value about day 100. And actually, we even have a lower mean wind speed than we did historically. Historically, the mean wind was about 1 knot. Now it's down to 0. So we're getting less mixing now, and the mixing that does take place essentially ends earlier in the calendar year than it has historically. Once again, encouraging the development of stratification in the Sound. This is just another kind of a plot. This is the August median wind speed. Here we have direction, degrees true, 0 to 360. This is 1960 to 2010. Again, this is at LaGuardia Airport. This is essentially winds out of the south, and you can see that the higher velocity winds are the dark reds, and you can see in recent years, going back to the 1980s, that the wind appears to be slowing down during the summer months as well. So what are the impacts from a changing wind field? Decreased wind speeds reduces water column mixing in the spring, extends the period of stratification, and in the summer, I neglected to mention, we've also had a change in wind direction. The mean wind direction has changed essentially from 245 degrees true to 215 degrees true. And if you look at the alignment on a map of Long Island, you'll see that 250 degrees true lines up very closely with the axis of Long Island Sound. And during summer, this increases gravitational flow or enhances stratification again. All right, so now I'm going to talk a little bit about the western Long Island Sound. And I want to point out these red circles. This is 1988, 1992, 2000, and 2004, I think. This is dissolved oxygen in the bottom waters in milligrams per liter. This is the record from 1940 to 2010. The New York City Department of Environmental Protection has records going back to roughly 1909, looking at temperature. Well, they didn't measure density very well at the time, but they got temperature records and they have dissolved oxygen records. So it's one of the richest water quality monitoring records that we have in the country. But my colleagues and I have looked at it from about 1945 or so up to the present time. And you can notice here that there's clearly a decline in the dissolved oxygen in the bottom waters of the western Long Island Sound over this 40 or 50 year record. Now, if you listen to a lot of people, they will tell you that, well, the decline in dissolved oxygen is relatively recent. It's because of the fact that we have more people, we produced more sewage, and things like that. But here we can see that this actually has been going on for about 5 or 6 decades. So what's causing it? This is, over the same time period, the difference in temperature between the surface waters and the bottom waters. And over that period of time, the difference has increased from about 0.5 degrees centigrade up to about 2.5 degrees centigrade. So what has happened? Anybody want to take a guess?
Not getting overturning.
Not getting overturning. Okay, that's right on. But why aren't we getting overturning? Is it global warming?
The water's warmer that they. from the
Okay,
sewage
where
treatment
is the
plants?
water warmer?
From the sewage treatment plants?
Probably not. But what water is warmer? Remember, we're talking about surface waters and bottom waters.
Surface.
Surface waters, because of global warming, you suppose? Or regional warming? The surprise is
I think so.
that the bottom waters are getting colder. This is the record of the bottom temperatures over that same period of time. And going back to the 1940s, it was about 19 degrees centigrade. Now it's about 16.5 degrees centigrade. So most of that delta T, change in delta T, actually is because bottom waters are getting colder. That seems weird. But based on what I told you before, it gets back to this business of mixing and stratification. We're stratifying the water column earlier in the year, so we're isolating the bottom waters earlier in the year, and so what we're doing is essentially we're isolating the winter bottom waters, which are colder, from the vernal warming that ordinarily would take place if mixing was going on into April, May, and June. So by changing the Hudson River flow, the changing characteristics of Hudson River flow and so forth, and increasing having stratification begin earlier in the year, we're isolating the bottom waters, creating this phenomenon where we see delta T increasing, and as a consequence, the reservoir of dissolved oxygen in the bottom waters that used to be there, left over from winter, is being used up over a longer period of time because we're starting stratification about a month earlier than is the historic norm. Am I making myself clear?
When you say bottom waters, below the thermocline?
Yes. These waters are essentially about 1 meter to 2 meters off the seafloor.
Cool.
You're shaking your head. You don't believe it.
Well, it's not that I don't believe it, I just, the depths of Long Island Sound vary.
Yeah. It's about 100 feet deep in this
Right.
particular.
The thermocline that I'm aware of is around the summertime, 10 meters.
Probably. Could go down to 15 meters.
So from 10 meters down to 35 meters, is that the bottom water you're referring to?
Well, this is closer to the bottom because we took the bottom DO is what we were concerned in. That's where we're getting the anoxia and so forth, and critters croaking. Yes?
With colder waters, would you originally have more dissolved oxygen? Does it?
Cold water has more dissolved oxygen, but probably the biggest issue here is that if you have think of Long Island Sound as the bottom waters below the picnic line as being a limited supply of dissolved oxygen for a fixed period of time. Now, if you extend that period of time over which that fixed period fixed volume of oxygen is there, you're going to begin to use it up earlier in the year, and so by the time you get to August, September, there's not going to be anything left. All right, so now I'm going back to the 4 circles. In 1988, let's see, back up a little bit. 1988 was a bad year. 2004 was a bad year. Relatively speaking, 1992 and 2000 were good years. And this is the wind characteristics, just to show the influence of wind on these systems. 1988 was one of the worst years that we ever had for hypoxia. And you can see that the prevailing wind was out of the south to southwest and moving in that direction, enhancing stratification of Long Island Sound by enforcing gravitational flow. 2000, during July, August, the wind field, for whatever reason, tended to be out of the northeast. And so we got breakdown of gravitational stratification and some mixing taking place. So the dissolved oxygen was replenished at some point a little bit relative to 1988. 1992 was another good year, and relatively speaking, and again, the winds were out of the northeast. And 2004 was extremely bad, and we had our southerly winds. The prevailing winds in our neck of the woods are out of the south to southwest. So these are more typical conditions, but just by having some unusual weather conditions taking place, we can see that you can break down stratification to some degree in the summer and enhance bottom water dissolved oxygen. All right, so now I'm going to change and look at this area. This area, remember, is not really influenced by sewage treatment plants. The only sewage treatment plant is one located in the Nisququag River right here, and it probably has about 0.5 million gallons per day discharge. Ward's Island, one of the plants in the East River here, discharges about 280 million gallons per day. So just to give you, the magnitudes are tremendous in the city. There's another treatment plant in here in Port Jefferson, but it really doesn't get out into Long Island Sound. But this always seems to show up as sort of a hot spot during summer. And so one of the things we wanted to find out was whether the University of Connecticut's single station, which is somewhere out in here, was representative of what was really going on, or whether their contours were exaggerated. You know, you guys are probably more familiar with it than I. Contour programs can make you think things that maybe aren't actually happening. So we wanted to look at it in more detail. So we had 3 or 4 years of intensive sampling over that scheme of things. Stony Brook University, incidentally, is right around in here, almost on Stony Brook Harbor. This will just give you a picture of the changing distribution with a falling tide and a rising tide. And the blue is low dissolved oxygen on the order of 2.5 milligrams per liter. And the reddish colors are close to 6 or 7 milligrams per liter. So you can see that it changes with tide, and it's quite variable over the spatial grid that we set up. And so the single point that the Connecticut monitoring program has probably isn't really representative of what's going on. And this is another year, 2009. Again, all bottom DO, and you can see the difference between the falling tide up here and the rising tide. So why would we have a hypoxic hotspot here, given the conditions that there's no real sources of pollution going into the area. Well, our hypothesis is that these two features are essentially serving as huge breakwaters. And if you've all been on a ship and watched waves between piers or fixed structures and so forth, you can see that you get some very strange current flow patterns. And our hypothesis was that these structures were creating a gyre in the system, and that there was not good circulation or anything that was in here to get out into the main part of Long Island Sound. We also thought that these areas, which are rich in marsh grasses, some of the most healthy wetlands on Long Island, contribute large quantities of organic material that get out into Smithtown Bay and probably don't get dispersed anywhere else. Gradually they sink to the bottom.
What is the depth of water in that embayment?
Out here, probably 20 meters. 60, 70, 60, 65 feet. And here is a model of the residual currents in the area. This is Crane Neck. You can see a great deal of confusion caused by that point of land. And this is over on the other side of Smithtown Bay, Eaton's Neck. Again, you can see that. This is residual currents with the tides removed. And you can see that there is a gyral system in here, and the currents get very weak as you get back into deep into the embayment. So circulation is in fact very poor there. There's one other source that we're just starting to look at now, and that is nitrogen releases from groundwater. The greatest source of fresh water to Long Island Sound from Long Island itself is groundwater. It's not from surface waters. And Long Island is famous for its septic systems. We essentially don't have very many sewage treatment plants in mid part of Long Island to the east end. And yet we have a population of, in Suffolk County, the eastern county, of about 1.5 million people. So we could be getting some seepage of nitrogen from septic systems through groundwater into this area, and we're just starting to look at that. So this is by station. These are the stations that are sort of in the center of the picture that I showed you. And I just want to show you a little bit about water column structure. This is the TS diagram, salinity down here, temperature here. These are lines of constant density. If your TS diagram, the plot of temperature and salinity as a function of depth, is parallel to these lines of constant density, you can mix the water very easily, right? If it's all uniformly mixed with regard to density, you can take a parcel from the surface and get it to the bottom, and it's gonna, it may go back up, it may not. But in these cases, during summer months, you can see they're perpendicular to the lines of constant density, so there is no mixing going on. So this is the fall, or the summer into the fall of 2010, and here you can see the evolution of the summertime water column from less saline, colder, to eventually you get extremely warm water, extremely salty water as runoff begins to taper off. And then this is September. That's when you typically get overturning of the water column. Nor'easters start to come in, you get mixing of the water column, and as a consequence, the bottom of the sound is reventilated and dissolved oxygen concentrations go up. So this is a typical kind of thing you see in Smithtown Bay. Very well stratified water column that doesn't allow any mixing. And this is a comparison of 3 different Augusts. This is August of 2009, 2010, I think. No, this is 2010, 2009, and 2004. And here you can see the importance of summertime climate. This was 2009. This was a wet year, relatively cool. This was an extremely dry year without much precipitation. So local precipitation and so forth plays a very important role in stratification of our local waters. But no matter what the weather conditions are in Smithtown Bay, we constantly have this very strong stratification taking place in summer. And this just gives you an idea of the kind of picture we have. The top here is the density structure. This is, the black is land, and or the sea bottom, and the dark blue here is low density water. Strangely enough, you get the low density water in the middle of Long Island Sound compared to close to the coast in this particular circulation system. This is dissolved oxygen. And here, the dark red is 7 milligrams per liter. The dark blues are closer to 3 milligrams per liter. And you can see very low dissolved oxygen right up to the surface almost, close to the coast. The center of the sound has relatively rich dissolved oxygen, but we have this lens of very low dissolved oxygen at the bottom going out into the center of the sound.
Where were these cross sections?
This was in the extreme east of Smithtown Bay, where I showed you.
Okay.
This one happens to be here.
Within that.
Yeah. And the lowest dissolved oxygen was right here,
It's closest to shore.
closest to shore. And very indicative of this counterclockwise circulation that we see there.
What is the tidal range in that area?
It's about 7 feet. All right, the last thing I wanted to show you before we talk about monitoring is that we haven't talked about the vertical structure of the water column very much, but the vertical structure is extremely important. And this is again the kind of thing that would be helpful if you guys could come up with a better way for us to monitor on a more continuing basis what the vertical structure is. We have used something called the Brunt-Vasela frequency to look at what the depth of the picnic line is. And basically what we're looking at is what is the percentage of the water column that's above the picnic line depth, the density stratification depth, relative to the total water column. And the red here is dissolved oxygen. And so it's about 5 milligrams per liter here, and it goes down to about 3 milligrams per liter at the bottom. The depth here is about 14 meters. But you can see how nicely it corresponds with where the picnic line or the rapid change in density is. And this is a plot of the calculation of the Brunt-Vasela, so you can see that visually they line up very nicely. I just wanted to point this out. The percentage, where the picnic line is in the water column is extremely important. And what happens is that if the picnic line is shallow, as it is here, 0 to 10%, you got a huge reservoir of dissolved oxygen below the picnic line. If the picnic line is very deep in the bottom third of the water column, then if you have any turbulence that takes place, such as a storm passing through, in all likelihood, the picnic line is going to bounce off the bottom, and you're going to get reventilation of oxygen from the surface to the bottom. And then where it's worst is when the picnic line is somewhere in the middle of the overall water column. And we see that not only here, but we see it off the Jersey Shore during summer when they have hypoxic events as well. So in this case, if the water column is, say, between 40 and 60%, if the picnic line is 40 or to 60% of the total depth of the water column, that's when we get the maximum extent of hypoxia. All right, so some of the things to look at with regard to monitoring. We need to improve the spatial coverage that we have for monitoring. And the kind of thing that one might play with, just off the top of your head, is that instead of spatially scattering our sampling stations around equally, maybe we should concentrate them in very critical areas. Maybe where change takes place more rapidly, one place relative to another. So we need to get more efficient use of the resources that we have by improving the spatial coverage that we have. Because we know we're not going to just get more bucks to go out and add stations. We need to optimize sampling frequency. The Connecticut people do it every 2 weeks. They do it during business hours. And is that an adequate reflection of what is actually going on with regard to hypoxia in the Sound or anywhere else? And we really need to know what's going on vertically as well. So, go back to this figure. Is there a way to optimize this number of sampling stations to give us a better picture of what's actually going on with regard to hypoxia? This is a week-long record of dissolved oxygen. You can see the variability. Every one of those peaks represents about noon to 4 o'clock in the afternoon. When we're getting peak photosynthesis, this is when we do most of our sampling, between 8 and 4 or 5 o'clock. So are we adequately representing what is going on with regard to dissolved oxygen if we're only going out during this period of the day? So we need to have tools that allow us to get continuous records at the locations that we're sampling, and not just going out with bottles every 2 weeks during business hours. And just as a conclusion, I think you could see this in the records that I had going back to 1940. Nobody really was thinking very much about how dissolved oxygen or the temperature structure was changing in Long Island Sound, because we had done so many things to Long Island Sound in manipulating it, hardening shorelines, dredging some of the harbors, putting in sewage treatment plants, etc., that those things sort of masked what was going on with regard to climate and what maybe the natural processes are. And I think now we're beginning to see that the things that we have done to the Sound in New York City and so forth, they're more or less becoming a little more stable. And we're probably going because of the change in climate, we're going to start seeing that processes are more visible, at least in terms of what climate is doing to drive these systems than what we have done in the last 100 years to modify them. So in order to do that, we definitely need better records, we need longer records, and we need records that are more continuous over time than we have been able to take so far. So I'll stop here and take questions, and also hopefully get some feedback to take back to the people that I work with on the Long Island Sound study. I should have said that I'm really here not representing Stony Brook so much, but representing the Long Island Sound study, which has funded a lot of this work over the years that I showed you today. Okay. Oh, questions, please. Yes.
I don't think you showed this, but how much has the aerial extent of the anoxic water, or close to really low hypoxic water, increased since 1940? You showed one curve of the
Right.
concentrations, but what about the aerial extent in the eastern, the western portion of Long Island Sound?
Well, that's been one of the things that's been difficult to deal with. The only records that were ever kept were those of the New York City Department of Environmental Protection going back into the 1940s up until about 1970 or 75. So Connecticut really didn't start their monitoring program until the early 90s. So we, other than the Western Sound going out, not quite to the Connecticut border, but only that portion we really have records for that go back to 1940. And you know, you guys are developing tools all the time. You've got to also remember that the tools that we had even in 1945, 1950 were relatively crude. We couldn't measure salt in the ocean very effectively until certainly the 1970s. So the spatial coverage is limited. Yes?
Can you go back to your slide that had kind of a 3-part wish list? Look, there we go. Optimize spatial coverage. Can you elaborate a little bit more on that XYZ type of?
Yeah.
I mean, these are all two-dimensional.
Okay. So, you know, this is the way most of the sampling is done now. They go out, collect data at these points. The question is, could we learn more about sampling if we put more buoys out here, or took more data out here, or took more data here, eliminated this? So, you know, what can we do to optimize that geographic distribution of stations?
Have you heard of the NU shuttle in Narragansett Bay?
No.
NU shuttle? It's a instrument that's towed
Uh-huh.
on the back of a ship or a boat. And it makes circular transects around the entire bay, but it goes down and up, down
Okay.
and up continuously. I think they, at least when I was an undergrad 5 or 6 years ago, they would deploy it once a month, and I actually used all that data to calculate seasonal flushing times
Mm-hmm.
for Narragansett Bay.
Okay, so I've heard of these undulating systems, yes.
Yeah.
Just not that name.
Okay,
Okay.
it's NU shuttle.
Okay, so that's a good idea, thank you. Anything else? Yes?
What about, so some chemists are uncomfortable with automated sensors, and they like to actually have the water to take it back to the lab. And I don't know enough about dissolved oxygen to know how difficult a measurement it is to make, but are things like optodes and that kind of stuff sufficient for the work that you need to do?
I'm suspicious of automated systems too. And we do calibrate the DO sensors against Winkler titrations. So we think we have a pretty good handle on it. But nevertheless, there are limitations, particularly when you have to consider you have to get out and clean the probes off and that kind of thing on a regular basis. That's time consuming, very time consuming also. Yes.
So another option, I suppose, I suspect there's a fair amount, I actually don't know, there's a fair amount of ferry traffic across the sound?
There's a ferry that goes from here to Bridgeport, and we have had sensors on that running continuously, and so we've gotten some very good flux data for water going this way and that way from that data set. And then I think the University of Rhode Island runs a ferry system from Greenport to New London.
I suppose that doesn't help you much with bottom water, does it?
No, we get surface dissolved oxygen, but we don't get bottom dissolved oxygen with those systems. Yes.
What's the time constant on most of these DO sensors? The ones I've used in the past have very long times to stabilize.
The ones that we have
So
now
you
probably.
stay at the same place for a long time and move very slowly and not smear out your
As fast as we can lower a CTD down to the bottom and up, the DO sensors now will accommodate that kind of speed. So we're talking about a few meters per second. They've improved greatly. That being said, you still have to calibrate to make sure that they're in the ballpark. Yes?
Is there a way that if you could trap the water and keep it there, would the DO degrade over time?
Yes.
It would?
So if you take, people do that rather frequently. They take a sample of water and they'll take it back to the lab and try to simulate conditions and then watch what happens to the biological growth. And I don't know if you've ever heard of it, but they have these things called light and dark bottle experiments where you can get respiration rates by looking at what's happening in the day and the night, essentially the difference. Yes?
Just a couple of comments on Val's point on the instrumentation. We had a buoy offshore here about 10 kilometers, an open ocean aquaculture site where we put in the DO sensors on a buoy system, surface, mid, and bottom. And we'd go out, I think it was about every couple of weeks, take Winkler, or samples for Winkler titrations for calibrations, and that, I think the combination of that works pretty well, and the sensors have improved. The second comment was, and I think you implied the answer, but you do have to have, I think, 24-hour monitoring of the dissolved oxygen levels because respiration or oxygen is used in during the night, produced in the day and then utilized during the night, so you have to have low periods. And the final point is the problem they're seeing in a much smaller system in the Great Bay Estuary and the Schaghticoke River in this region, which is again a multi-million-dollar question, but issue is the balance between point sources like sewage outfalls and the diffuse sources which you alluded to by Port Jefferson from surface runoff, and also which I would consider probably a major input is atmospheric inputs.
Yes.
In terms of addressing the hypoxia and anoxia, the multiple sources is a large issue.
We have estimates for atmospheric contributions that go into a relatively sophisticated model that's run by New York City and the Long Island Sound Study for trying to make value judgments about implementing total daily maximum loads. One of the things with the total daily maximum loads is that has come up frequently is the equity issue. When EPA imposed the TMDLs, they said, okay, you're going to have to reduce a certain percentage by such and such a time, And we don't care whether you're a secondary sewage treatment plant or a tertiary sewage treatment plant. So Stony Brook University had the only operating tertiary sewage treatment plant until very recently. We still had to reduce that tertiary effluent by whatever the percentage was, while the city, which was several hundred times the volume, had to only reduce it by the same percentage, and they were only secondary treatment. So there was a lot of issues about equity. Is it fair to take a small community in Greenport out here and say they have to do the same things as the city here? So that's one of the things I think where it's important that we truly understand the processes that are feeding this hypoxia issue and where we get the biggest bang for the buck. For example, in our case with Stony Brook University, we're here. Our effluent goes to out in Port Jefferson Harbor over here. Well, if you look at utilization and within Port Jefferson Harbor, there probably is no nitrogen coming from our sewage treatment plant out into Long Island Sound, but yet we still had to reduce it. We believe that that sewage effluent, the nitrogen in it, is being all internally recycled within that little harbor. Any other questions? Yes?
So if you wanted to go about improving your spatial sampling model, what would be the things you would want to take into account?
Well, certainly, just spatially, I think the question is, are we buying an awful lot by continuing to look at these areas where now we think things are pretty good? On the other hand, you'll get the argument, well, things may go to hell in a handbasket, so we got to keep looking. But I do think that, you know, probably ought to do more here. We probably ought to be paying more attention with regard to ultimate management of the sewage treatment plants of what's going on in these little harbors. And they're being totally ignored in the planning for all practical purposes in Long Island Sound. But yet, New Haven and Bridgeport, Norwalk and Stamford all have significant sewage treatment plants that probably are influencing the sound here, but back in the bays. We should be able to say what the load is from that treatment plant, not only immediately within Stamford Harbor, but how much of it is getting out here.
I'm surprised the EPA doesn't make each sewage treatment plant do that. They have to reduce it to a certain level.
Monitoring the harbors, the Long Island Sound Technical Advisory Committee has constantly told EPA we should be doing. And the reaction basically it has been that we really can't afford to do that. And so they're relying on citizens monitoring. And you know, that opens up a whole other kind of Pandora's box about technologies used, calibration, QA, QC issues, that kind of thing. Yes?
I know Norwalk wastewater treatment plant is going through an upgrade right now to reduce nitrogen output, and I noticed there's a little bit of a bulb there at the Norwalk outlet of higher DO or lower DO levels.
Right. So that's between 3 and 3.5 or something like that.
So that is something that's happening.
Yes.
That's going to help reduce this issue.
Hopefully.
Hopefully.
Yes. So the treatment plants in Port Jefferson, in addition to Stony Brook, are also going to tertiary treatment. Probably won't do any good in that case. So it'll be interesting to see what happens with Norwalk. Yes?
I was wondering in that area by Smithtown where you see that sort of hot spot, and you were trying to figure out where the nitrogen was likely coming from, whether it was groundwater or the wastewater effluent. Have you tried any like sort of tracers to see where the water from the wastewater effluent plant is ending up?
We have, not sort of indirectly, and I think I mentioned when we were at lunch, we've used iodine 131 as a tracer. And the reason we've used iodine 131 is that Stony Brook has a hospital, and they're a regional center for treating thyroid cancer. And as a consequence, the concentrations of iodine 131 in our sewage sludge and sewage effluent is relatively high. And in fact, as I mentioned to you, it's the highest that we've seen reported in literature. So it's a good tracer. And we have used that as a tracer around the harbor and out over to here. And essentially what we're seeing, what we saw in that case is that very little evidence that there's anything getting out of here and going west. And there may be a good reason for that, because again, if you think of the estuarine flow, in bulk, the fresh water is going this way at the surface and the bottom water is going this way. So there might be a little more over in this direction than here. But we were interested in Smithtown Bay. Yes?
If you supplement the existing network with some gliders, or kind of give you a good...
We're part of the Maracus, or whatever it's called, the ocean observation systems. But the Long Island Sound study has not gotten very much money out of that program. Most of it's gone to coastal New Jersey down here. So we have not, we would like to use them, but we have not been successful in acquiring any. I know Jim O'Donnell would love to have a bunch of gliders. Okay.
One other question. Yeah. Is the scale of the problem such that any engineering applications would have no chance of having an effect on this, or are there potential future kind of engineering modifications that might improve the overturning or the circulation? Or?
Well, we've gone through a lot of soul searching with regard to Sandy. And there have been proposals to build tide gates. And one proposal is to put a gate close to the Throgs Neck Bridge near the entrance to the East River, and then others at the entrance of New York Harbor at Sandy Hook. But prior to that, there was a proposal by Dr. Malcolm Bowman at Stony Brook that we should put a tide gate at Throgs Neck to improve water quality. And the idea would be that on when water is flowing from the East River into Long Island Sound, that the gate would be up. And then when it flowed the other way, it would go down. It would go towards the harbor. And in addition to the expense, New Jersey started to complain, as they always do, that New York is flushing once again on New Jersey. So it hasn't gone very far.
Well, wouldn't that be true, though? I mean, essentially saving
The dilution. It would be true, yes.
Sacrificing New York Harbor and saving the Sound may be a hard
Right,
sell.
yeah. And that's the kind of thing too we're going through with building tide gates for around New York Harbor. Who's in and who's out. And we as scientists, I think, very often forget the social aspects of these questions.
And the bigger technology is what Kirk proposes in the sewage treatment and the effluent, and keeping that at a very low level, nitrogen coming in, but that doesn't
Right. One of the most successful things that I think that has occurred with New York City is that if you go back to the mid-1980s, we had a pretty severe drought in the city. And there was a very concerted effort to reduce water consumption. And it was highly successful. New York City lowered its sewage effluent discharge from about 1.8 billion gallons per day to 1.5 billion gallons per day. And that has allowed the treatment plants to improve their operation. And if you think in the really big picture, 300 million gallons per day is the size of the largest sewage treatment plant the city has. So it's an avoided cost by conserving water of the expense of building a plant perhaps that's about 300 million gallons a day. And I don't know what it costs to build a sewage treatment plant today, but I know when they built the North River sewage treatment plant, we're talking, $1 billion or so. Yes?
Yeah, I naively sort of thought that in the olden days, maybe 40 years ago or more,
Hey.
That was cold, man.
I'm over that age. That most of the sewage was actually not treated very much and was just pumped into major bodies of water, and that yeah, well, and that of late, in the last, since then, that more treatment plants have come online, and maybe the population has gone up, but I've never really known how to gauge whether the population was rising faster than the capacity to treat water, and whether or not the treatment of water really has any effect, or even if it removes nitrogen.
Interesting question, and if anybody wants to leave, feel free to leave, but this is one of my favorite topics. Up until 1987, New York City still discharged 450 million gallons per day of raw sewage. Didn't go through a sewage treatment plant at all. And included in the buildings that were not sewered were the World Trade Center and the headquarters for US EPA. So when the World Trade Center was still there, you could go up to the upper floors and you could look out and you could see the plumes of raw sewage going out into the Hudson and the East River. In 1987, the city completed their last two plants. It was the North River plant. I think it's up around 100th Avenue or whatever, and the Red Hook plant in Brooklyn. Going back to 1972 with the passage of the Clean Water Act, we were required to go from primary treatment to secondary treatment. Now, most of New York City's treatment plants where they had treatment were already secondary, but they improved the level of the secondary treatment. The impact of that actually could have exacerbated the hypoxia problem in Long Island Sound in the following way. More organic matter was going out into the East River 40 years ago with secondary treatment, but not as good a secondary treatment as we have today. Now we've changed the form of nitrogen so that it's more available to critters and it's in a more dissolved state. And so it is being transported more readily to this area that's highly hypoxic. So over the years, by improving sewage treatment plant operations, we could have exacerbated this problem. If EPA was in the room, they'd deny it, but it's certainly true. So another thing that has been a problem with regard to the nitrogen is that, I don't know if any of you all have ever heard of it, but we used to take sewage sludge, that's the residue from the sewage treatment plant that has more solids in it, and we would put that in a ship and we took it to sea. Well, there was no nitrogen removal in that. But when the EPA said there would be no more ocean dumping in 1988, the city was faced with, now we have all this sewage sludge. It's 95% water. We can't afford to ship it around the country. What are we going to do with it? So what they did was they built a series, there's about 6 centrifuges at several of the sewage treatment plants. So they centrifuge the sludge now, and the solids are retained in the centrifuge. The centrate, which is rich in nitrogen, is spun off to the side. That is put back to the head of the plant. That centrate is so rich in nitrogen that it increased the level of nitrogen in the plants by about 25 to 28%. So if you were to look at the concentration of nitrogen in the effluent in 1991, you would see it would be at a certain level, and 1992 it was a certain level plus 20%. So, you know, we had EPA saying you got to improve the situation in Long Island Sound, and by the way, you got to end ocean dumping, and as a consequence, we don't care what you do, but you know, just do it. And it was very expensive to start bringing those levels down. Yes?
You know, I keep looking at this map you've got here that you're showing, and that's almost a synoptic view on August the 3rd, 4th, 2010.
Yes.
So there's a series of those, because you said those go out every 2 weeks.
Yes.
What would happen if you had a movie of showing that slice, those synoptic views, through the year or 2 years or 10 years, however long they've been doing this? How would those boundaries move around? Between the red and the brown and the brown?
It would be an interesting look. I haven't looked, but...
Because this might be, I mean, is this really typical of what
yes.
a synoptic view looks like?
Yes.
Those
In fact,
boundaries
this
don't
is better than normal, this one. This was August. If you go back to the other one, which was, I forget what year it was, 2004 or something, it was much worse than this.
But it'd be interesting to see, I'd be interested to see if there's any dynamics to those boundaries. That's probably telling you what's going on.
Time series.
Yeah.
A time series,
Yeah. We do have that, and the Connecticut people display it in a different way. What they display is they put out a graph that shows what the aerial extent of certain ranges of dissolved oxygen over the period of observation, 20, 25 years, whatever it is. So we have a continuous record of that, and but it doesn't show you where necessarily.
Yeah, because I would ask the question, if the boundary is fairly stationary over is it a decade worth of data?
It goes back to probably 1991, 1992.
Yeah, so a couple of decades. If that boundary doesn't change, the first question I would ask is, what's the bathymetry in that boundary zone look like? Is there something in the bathymetry that's affecting where that is?
Well, what we know that it's a very deep channel coming out through the East River. And the currents in the East River are on the order of 5 knots maximum.
In the river, yeah.
In the river. And so you get very good flushing down here, and it spits out into here. Now, Long Island Sound is a co-oscillating tidal basin. So at the race, the range is very small. Down at Throg's Neck, it's very large. So it dumps out into this area where the horizontal movement of water is essentially zero.
Yeah.
And it just sits there and cooks. So we know from the circulation that if you put organic material in here in the surface waters, which essentially sewage is, it will go out here and it just won't get widely dispersed, and it'll start to feed the plankton and what have you and sink to the bottom. But the bathymetry, I don't think anybody has looked at other than the bathymetry is there and it's part of a hydrodynamic model.
Because that pattern in this one just looks like it's being mixed by benthic, I don't know whether it's eddy diffusion or flow or whatever, but it's a nice gradient going from zero oxygen out to normal
Right.
oxygen conditions. So it's a nice, it looks just like it's a simple diffusion problem, a mixing problem.
Yeah, so that's a great suggestion, though. See if we can maybe do something
Make
with
a
that.
movie, yeah, it'd be really easy to do.
Yeah,
Yeah, 'cause
cool.
the opposite occurs in the far eastern end there. Fisher's Island race, I mean, you've got tremendous mixing going on there.
Yep. Yep. Okay, I kept you guys too long. Thank you.